Good morning. It's Morning with Meep. And today I want to talk about model risk. I'm just going to do this at a high level. The reason I'm getting into this is because I've already done one part of this, and that relates to data. To begin with, being a geek myself and having degrees in math, let's start with definitions. What do I mean by a model? And and I could show you the picture from when I modeled for a furniture ad, but let's get serious for a moment. So model is a simplification of reality. It does not need to be mathematical, by the way, but generally it's implemented in some kind of mathematical formulation in terms of formulas or certain kind of formal structures. In general, you are trying to analyze or forecast or predict all sorts of things you can do all sorts of things with models, but you're trying to match reality in some way. And maybe it's theoretical, something that hasn't happened yet, but again, you do this because, and the reason it's a model, it's like a toy version, a skinny down version, and you hope it's complex enough to be able to give you results that you can use for real life purposes, such as decision making. Okay, that was a lot of words, but most of the time we understand what is meant by a model. A lot of times models are shown in public for forecasts, but very often models are created to try to fit something from the past or something that has already occurred to try to analyze maybe cause and effect chains. There's all sorts of reasons you might have a model to try to fit to something in the past. It does not necessarily mean you're trying to predict something in the future. So what are main huge categories of model risks? I've already talked about data, and there were a couple of videos I did on Know Your Data. I was talking about COVID-19 data specifically, but this is true in general. This has become a problem with regards to data science getting its little tendrils in all sorts of quantitative fields. You have to know your data to be able to make any kind of sense out of it. I don't care what kind of model you're using. My favorite story is an actuary I know who's in property and casualty, who was talking about data science people coming into P&C insurers, but not really understanding the business of insurance. And they had their great predictive model, and I don't know what kind of regression or decision tree or whatever they used, but they came back with very useful information that if you use policy year X, and I'll just make up an X, say 2013, that's where the profitable business was. So all you had to do was go back in time, get your time machine, go back and write more business in 2013. Needless to say, this is not a useful analysis. Other aspects of insurance that these data scientists did not understand was deductibles and why they exist and how they behave, and all sorts of other things, which of course actuaries have to know. And a lot of you don't have to be an actuary to know this stuff. Data scientists can learn this, but to be really effective in modeling, you really have to understand what's going on with the data and what you're seeing. The next problem is structure of the model. Now, I'm not getting into the philosophy of modeling, and people say, oh, picking the structure of the model is really a hyperparameter. Yes, it is, and I really don't want to get into that right now. That said, there's always some kind of structure to a model that generally you're going to pick, and then it goes on from there. I've seen this with the COVID models that are being used. Many of them are what are called SIR models, susceptible, infected, and recovered. I've seen SEIR models, and I can't remember what E stands for, but the concept is there can be preliminary states to being infected. In any case, it doesn't matter. That's a structural choice. You can have structural choices. I've seen this with models to try to, say, do the S&P 500 index. A lot of people are familiar with log normal models for finance, but there's also stuff like regime switching for volatility. So let's say you have a high volatility regime and a low volatility regime. Each of them is like a log normal series, but it's a log normal process in both cases. But you may switch from being the low volatility, so normalcy, versus high volatility, which is right now, and having that kind of thing. You can also have stochastic volatility equity models, and I've seen those. There's a lot of different structural choices. These are not necessarily right or wrong, though sometimes if you pick a structure that really doesn't fit what's going on in the real world, this can cause a lot of trouble. The one that example here, and I will do a lot more of these later, has to do with something called copulas. And copulas are a way to get random variables to be correlated in a certain way. Well, part of the financial crisis from 2008 came from using what are called Gaussian copulas, which is not how the real world works. Again, I'll talk about it another time, but there was a key aspect of that structure that failed with regards to how these models were being used, specifically in a crisis situation. The tail risk, so that's like a crisis situation in the tails, the Gaussian copulas do not work well. That's all. Okay, so that's structure. Next one, parameters. Once you pick a structure, so I mentioned log normal, stochastic volatility, regime switching, those kinds of models. Once you have a structure, usually there are parameters, so items that you're going to take that data and then try to fit those parameters. So aspects of the problem with parameters is there's never one way to fit the parameters. And then some of the problem has to do with how sensitive those parameters are to the data you're fitting them to. That's number two. Sometimes you can't observe anything to get these to fit, or there's basically an infinite number of parameter sets that fit equally well, and generally there are. So sometimes you make assumptions about how these things work. I'll give you an example. From the COVID models, you make assumptions of how the R0 or RT behaves under lockdown versus no lockdown. Okay, so those are some of the parameters. Some of them are just, you can't fit them, or you fit them to a different data set from what you are going to be trying to replicate. This actually happens in the insurance world if you have a new risk, so say cyber liability. Sometimes you try to figure out what is an associated risk that might behave the same way as cyber liability. And so I'm going to use that structure. I'm going to use maybe those parameters, or I might do some sensitivity testing with those parameters. So parameters, again, I'll get into a lot more detail in a later video. So I just want to hit these at a high level. The next one is implementation. One of the first things that I really got into with regards to numerical computing, because that's how most of these models are implemented. Some models have a nice, what we call a closed form solution, where you have a nice formula. You don't actually need a computer per se. You know how it behaves. You might use a computer to, graph the curves and that kind of thing, but there's nothing really involved in trying to get the results out of the model. I had my own implementation problems when I was modeling neurons. The models I was using, and I don't want to get into it too much, involved generating a probability distribution, and I had differential equations that talked about the evolution of that distribution. So I would start with some probability distribution using the differential equations. That means I needed to numerically integrate to get, the next time step of where that probability distribution would evolve to. Well, in my implementation, so I had to code it myself, I kept getting negative probabilities. This isn't quantum mechanics. There are no negative probabilities in what state a neuron is in when I was doing a phase model of a neuron. Okay, that's enough geeking out for that. So I failed on that implementation. I never finished my PhD thesis, so there you go. And I don't think anyone's ever going to follow up on what I did, but maybe someone else came later and did it. I don't really care. But implementation is often a place where people don't pay enough attention because a lot of modelers are not experts in what I would call numerical computation. I took numerical analysis classes, but well before I took numerical analysis classes, I was trying various numerical algorithms to solve just plain math problems, but these are the kind of problems you have to solve in order to, implement certain kinds of models. And one of the first things I worked on was in high school. I was an intern to a statistics professor, and I did some Fortran code for him where I am trying to calculate various probability distributions. The problem is it was probability distributions like hypergeometric and binomial, where you have combinatoric coefficients, basically extremely large numbers being multiplied by extremely small numbers. And you can get both the problem of overflow and underflow. I won't talk about that another time, but I have seen this with a lot of modelers, especially in physics, that they know just enough technical stuff to get themselves into trouble and not understand why their numerical integration approach was not working. And then here is the final one. And this is not, I guess, specific to models. It's just a problem that technical people have in general. We get our results, we analyze. Let's say we fully understand what's going on. We understand the dynamics, we understand the results that are coming out, and everything else is fine. And now we have to present to, say, politicians or non-technical people in general. And we have to convince them to take an action or not take an action, as the case may be, or not overreact, or here are a bunch of choices and here are possibilities, and we are misunderstood. Okay. I might talk about that separate too. One of the aspects I like getting into is data visualization. It's a big thing for me because so much, and of course when I said I model neurons, it was neurons in the visual cortex, and a lot of brain power is taken up by our visual processing, just the whole machinery that's in our cortex. A lot of it's actually done in the retina itself, but anyway, the whole point is data visualization. When you have a very good graphic that shows results or really can communicate the results, that can be more decisive than using a lot of words, even for people who are more comfortable with words than numbers, because humans in general are extremely visual. But there are many ways you can be misleading in a visualization, but also if you use visualizations that are unfamiliar, they may be misinterpreted, even though you are not trying to deceive anybody at all. Okay, so I will do some videos on these different aspects. As I said, I've already done some videos on data risks with models. I think the next one I will try is implementation, because I've actually written about dangers of floating point, and I also want to talk about Monte Carlo or stochastic modeling, which often has pitfalls for people who are not used to it. And it's also one of my favorite modeling subjects because I'm very into probabilistic modeling. Though the probabilistic modeling I did before was not Monte Carlo, though now that I'm thinking of it, I probably should have done Monte Carlo instead of what I actually did, which was try to use the differential equations to evolve the probability distribution. Oh well, it's 20 years later. Who cares? So I'll see you next time. Bye-bye.